Assalamualaikum brothers and sisters. So today I am going to explain about the next amplifier for MOSFET, which is the common drain. Okay, so for common drain, the output is measured at the source terminal, as you can see over here, and the gain is a positive value. So for your common source, we compare with common emitter, right? So for common drain, we are going to compare with common collector. Okay, so similarly, you are going to rearrange the AC equivalent. Okay, so this is the common collector AC equivalent. So you can see the rearrangement over here, right? So it is similar for your common drain, but the good thing is you don't have to worry about R pi. So because there is no R pi in this circuit, okay, you can see that the steps here are simplified. You don't have to do step number 2. You don't have to do RIB. And that's it. So you are left with only the 3 steps. And in this case, the RI is your RTH. Okay, for common drain, RI is the resistor that is connected between gate and ground. Okay, so that's your RI, right? So as I have explained in the previous slide, there are only 3 steps. Okay, for your common drain, and then of course you have to find the AVOC. Okay, so let's look at one example. You can see this is a common drain amplifier. Okay, because the output is measured at the source terminal. So this is source, this is gate, and this is your drain. And your drain is directly connected to the power supply. Okay, so you have to do your DC analysis first. To find the AC parameters, you are given lambda 0.01 volt to the power of -1. And so you have calculated your VTH, okay, the Thevenin equivalent. Okay, so these are the steps to find your drain current. Okay, so you have to do the 5 steps. Okay, so you obtain 2 drain currents and make sure you obtain 2 VGS. But which VGS you're going to choose is the one that is 2.34 because it is bigger than VTN. Okay, so that's the one that you are going to choose, which means that the ID is this ID. Okay, the 8 milliampere. So don't forget to confirm your assumption, and once it is confirmed, then you can calculate what is GM. Because there is lambda, you have to find out what is VA. VA equivalent to 1 over lambda, and R0 is equivalent to VA over ID, which is 100 over 8, and that's how you get 12.5 kilo ohm. Okay, so that is how you obtain the AC parameters. Okay, so this is the original AC equivalent. You can see over here the V out is measured at the source terminal over here. And then similarly, you are going to rearrange so that V out is on the right hand side. So I bring my RS over here. You can see this is V out connected with ground. So this is my source. Okay, so this one is done. Then R0 is connected between source and D. And because D is grounded, so this is source and D, which is grounded. Okay, so this is ground. And then the next one is the GM-VGS. Source and then the ground, okay, D, ground, and the arrow is pointed towards S, okay, and there is nothing here, so you can see there is nothing over here, but VGS is measured between G and S, gate and source. Okay, so that's your VGS, and VI is measured between gate and ground, right? So let's look at the first step. Similarly to your common collector, I have labeled this as R equivalent. Okay, so R equivalent is equivalent to the small R0 in parallel with RS. Okay, and you obtain 0.70755 kilo ohm. Okay, so your output side is now simplified to look like this. Okay, so this is your R equivalent. Okay, and the current will flow in this direction. So that's why your V out is positive. So this is GM VGS, right? Okay, so you can see GM VGS multiply with R equivalent. Just use Ohm's law, and you obtain 8 VGS. And then for the super mesh, Okay, so you do the loop over here. That's why I get VGS plus Vout minus VI. And you obtain this equation. And that's why VI equivalent to 9 VGS. Okay. So that's how you obtain the equation for the third step. And then next is calculating your AVOC. We know that from step number 2, Vout equivalent to 8 VGS. VI is 9 VGS. Okay, so AVVI equivalent to Vout. AVOC, VI equivalent to Vout, right? AVOC 9 VGS equivalent to 8 VGS. So you can cancel VGS. Therefore, AVOC equivalent to 8 over 9. Okay, so that's how I get AVOC equivalent to 0.889. Okay, so now that you have obtained your AVOC, you can connect the voltage amplifier block with the input signal. Okay, because there is no load, AVVI is equivalent to Vout, right? Okay, so you can see AVVI equivalent to Vout because there is no load, and VI you have to use the voltage divider, right? That's what I did over here, and just replace in VI and you get Vout over Vs equivalent to 0.885. So you can see that this is less than 1, which is similar to common collector, right? Because common collector, the voltage gain is less than 1. Why? Because it is used for current gain. So similarly, common drain is also used to amplify current. So you can see over here, the R0 for common drain is calculated using a formula just like your common collector. So this next 2 slides is showing you on how to derive the output resistance formula for your common drain. Okay, so similarly using test voltage. Okay, and you obtain the output resistance equivalent to 1 over Gm in parallel with Rs in parallel with the small R0. Okay, for common collector, the R0 equivalent to R pi over 1 plus beta in parallel with Re in parallel with R0. Okay, the small R0. So in comparison, the Re is the Rs, and again there is small R0 over here. The only difference is the first term. Okay, R pi over 1 plus beta for the common collector, but for common drain is 1 over Gm. Okay, so now let's look at another example. The question asks to calculate the voltage gain, and you can see that the voltage is measured at the source terminal, and this time you have the load resistor RL. Okay, so in this case you can see that the FET is biased using current source over here, which means that you are providing the FET with the current that you want. Okay, so which means that I is equivalent to the drain current. Okay, and it is given as 0.8 milliampere. Okay, so you don't have to do your DC analysis, and you can straight away calculate your AC parameters. For your GM is equivalent to 2 KNID. Okay, so 2 square root of 1.25 multiplied with 0.8, and you will get 2 milliampere per volt. Okay, so because there is VA, you have to calculate the small R0. 100 over 0.8 is equivalent to 125 kilo ohm. Okay, so those are the AC parameters. Okay, so let me do the AC equivalent, gate, drain, and source. Okay, so you have your current source over here. Okay, and we have R0. So the drain is directly connected to the 9 volt, which is off during AC, and then straight to ground. And for your source, it is connected to the current source, and the current source is open circuit during AC, and then the minus 9 volt off. So this is open circuit, right? Okay, so my output is measured at the source terminal. So if I rearrange, I'm bringing an open circuit to the right hand side. Okay, which is what happened here. Okay, so actually this is an open circuit, alright, which is the source, and then I bring my R0 as well which is connected to ground, and then I have my current source connected to ground, and then the 100 kilo ohm, which is my RG just now, right? So just follow the steps. So R equivalent is equivalent to just the small R0, 125, and then the Ohm's law, GM VGS R equivalent is 250 VGS, and then the super mesh is VGS plus 250 VGS is 251 VGS. Okay, so this is the super mesh. And then the AVOC. So you can see that I am cancelling out my VI. So AVOC equivalent to 0.996. Then we can connect the voltage amplifier block to the input signal. So you can see there is no RS. Okay, it is connected straight away to the input signal. However, this time you have RL. Okay, so for the output side, you have to use voltage divider. So since we have RL, we have to calculate R0. Okay, using the formula, you can calculate what is R0. Okay, and we got 0.886 as the voltage gain. I can see that R0 equivalent to 0.498 from this answer here. So you can see over here, because there is no RS, you can ignore this term. So R0 is equivalent to 1 over GM in parallel with the small R0, right? Which is equivalent to 1 over 2 in parallel with 125. So what I have is 0.5125 over 125.5, which means that I will get 0.498 kilo ohm. Okay, so that's how I get RL plus R0 equivalent to 4.498 kilo ohm. Okay, so you get the voltage gain 0.886. So the next slide is just showing you on how I can calculate current gain. So I0 is equivalent to V out over RL. Okay, this is Ohm's law. And then your I in over here is equivalent to Vs over Ri. Okay, and we know that the current gain is I0 over I in. Okay, so V out over 4 over Vs over 100. And when you rearrange, this is your voltage gain that you obtain. And you get a high value of current gain, 22.15. Okay, so once you get your voltage gain, you can use the value to calculate your current gain. So similarly, just like your BJT, I have the summary over here for your common source and common drain. So you can see that your Ri is the same for all. And then for your common source, your output resistance is always the equivalent resistance at the output side, right? However, for your common drain, you have to use the formula. Okay, so that is the end for chapter 7, the FET amplifier. So thank you for listening. Bye. Assalamualaikum.